Okay, let's continue to study on principle of virtual work. So, in the last class, from the carbon equation of solid mechanics, general three-dimensional case, we derived the principle of virtual work, right? So, let's review and think again. So, so solution procedure was originally to find the solution. Find the solution. Solution means displacement, strain, and stress, right? That satisfies equilibrium equation on body and force boundary condition, which is equilibrium equation on body surface and boundary condition on surface, displacement boundary, and also material law. CIJKL. This is a material law for linear elastic isotropic material, right? So to find the solution, we need to use these four equations, right? But we changed the problem. How? Something like that. Find, let's say, displacement U such that this equation is satisfied. It's an integral type equation. Ij equal for all U. So now the procedure to find the solution is changed. So description of problem is changed. Maybe you are not familiar with this kind of new form. So first of all, let's look at the first form, right? You fully understand this, right? These are carbon equations. So solution should satisfy the carbon equation. So if we find some solution which satisfies the carbon equation, that just become a solution, right? So this was the original description of problem. Now the other description is this. This is a principle of virtual work which derived from the old carbon equation here. And we have only one equation, right? This one, integral type. Okay? Internal virtual work, external virtual work. So find UI, okay, which satisfies this equation. So very important thing is this one. For all virtual displacement pattern. This is virtual displacement. right? For all virtual displacement. So we said virtual displacement is arbitrary. So it can be anything, but should be continuous and should give us zero on displacement boundary. So here, all possible virtual displacement. If there is just some displacement u, which satisfy this equation, left side and right hand side the same for all the possible virtual displacement, then that become a solution. So it's quite different description. So this equation should be satisfied for all virtual displacement. It means this is not only one equation. Okay, it's a lot of equation, right? Because this equation depending on the virtual displacement, right? That's a really, really different description. So we are saying this is a strong form. This is a weak form. Okay, and here for linear elastic case, this part become changed, right? Eij, Cij, KL, KL, something like that. So it's really, really important to understand both forms. Strong form and weak form are equivalent. Same thing. Same thing. Exactly same thing. Okay? So, to find the solution, we can use strong form. Also, we can use weak form. Now you don't know how to use weak form to find the solution, right? Any question? Okay. This is most important. Now let's drive the principle of virtual work for truss case. Truss is a bar element. So bar member. Okay. So let's say we have a bar here. And here x equal 0, x equal L. So length become L, right? And here distributed axial force Q is applied, right? Then we can directly use that equation. So for this bar problem, the left-hand side, what become a internal virtual work? Internal virtual work. Bar have a stress only XX, right? Stress XX. It become P over A, right? So here, instead of this term, we can use P cross-sectional force P over A, right? Here omega, and strain. Strain is a stretch, right? Let's say here, displacement U1, here U2. So strain XX become U2 minus U1 over L, right? So virtual strain is similarly delta U2 minus delta U1 over L. Let's say this is just let's say this is just a strain. So left hand side become strain XX d omega. And here this means integration along the length and on the area A, P, EX, d omega and dx become, so on the area, this part is constant, so this becomes just 0 to L, so 0 to L, P, EXX, dx. So left part changed, something like this. So that's internal virtual work for bar. So again, internal virtual work for bar, 0 to L, EXX, P, dx become, how about this one, body force? Body force comes from the Q, right? Q is a force per unit area and unit length. So originally that equation for calculate from the integral about volume, but now it can be changed. Integral about the x-axis, right? So that part become 0L Q is a function of x and del U, let's say x dx plus on this bar, force can be applied. So let's say here P0 and PL. Watch this. This is a surface force per bar, right? So this part can be calculated from this part, surface force. Okay? So in bar case, surface is just a single point. So we don't need to integrate. So U, L, and that, let's say that is a P, L minus U, 0, P, 0. So if we use the general principle of virtual work, we can derive this simple equation. Let's say this is n instead of n. So here n. Because the p and n should be the same. N is the nodal force. So from the general three-dimensional principle of virtual work, we can calculate the principle of virtual work for bar member, right? Of course, you can derive exactly the same equation from the equilibrium equation for bar. You remember? Okay, so let's derive the principle of virtual work from the equilibrium of bar. You know, equilibrium or equation for bar is dx dp plus q is 0. This was the equilibrium equation for bar, right? And here we are multiplying virtual displacements. So P, Q, all the variables are function of X, right? Bar is a one-dimensional element, so everything is changed on X. So now let's dP plus, let's multiply virtual displacement. This is function about X, okay? Then it should be 0, right? And if I integrate here from 0 to L dx, it should be 0 too, right? And here, this equation have two terms, L dx dp delta u plus q u dx equal 0. 0 L. By using the integration by part, this part become u p 0 L okay, and minus 0 L p dx. So if I rewrite this equation, 0 L partial x u p dx, this is internal virtual work, and external virtual work become 0 L dx plus du p 0 L. So this become virtual strain in extraction. So this term is the same over there, and here let's say PL equal NL. So okay, nodal pulse is PL at the node. P and L is the same. So this term become this term. So even we drive the principle of virtual work for carbon equation of bar, we can have exactly the same equation, which is obtained from the three-dimensional principle of virtual work. So here, this is internal virtual wall. Okay, due to the virtual strain and internal force, and right hand side is external virtual wall due to the distributed load. This is a body force and force at the surface. So in bar case, at both ends here, left and right side, left hand side and right hand side. So this is a force described at boundary. So if the virtual displacement satisfies this is 0 on the boundary in left hand side or right hand side, this can become 0. So this term depends on how to apply the boundary condition. This is depends on this term depends on displacement boundary condition, right? So if our displacement, okay, so if that bar is fixed left hand side here, so here delta U0 equals 0, okay, we need to delete this one. We need to delete this one. Then boundary condition is already applied. So boundary condition is applied in this way. Okay? So in other words, on the bar, boundary condition is applied here. Okay, here there U L equals 0. We delete this one. This weak form is quite interesting, right? Okay. Now let's derive the principal virtual work for spring system. What happened? Principal virtual work for spring system. Okay, so this is a spring. So we have here U, U1, U2. But actually, bar and spring are same, except for only one thing. What's that? Spring cannot have a body force. So force is only applied on the both end. Left end and right end, right? That's the only difference. And here, force applied F1, force applied F2. And spring has a stiffness K. And internal force is a P. P equal KE. And E equal U2 minus U1. Right? This is the equation for spring. P is a positive for tension, negative for compression. So spring system doesn't have this part. Distributed force cannot be applied, right? So it it can have only 3 terms. So, for the spring principal virtual work from 0 to L, P dx d delta U dx. This is internal virtual work, right? Actually, when we define the spring doesn't have any ranks, right? Don't need to have a rank. So here, this integration become P L U2 U1 dx. So if I integrate this term, actually this is a strain, right? So this strain is constant through the rank. So this term just become P delta E. We don't need to perform the integration for the internal virtual work. So for the spring system, internal virtual work just become P, and this is a virtual stretch. You know the stretch. This is a stretch. So virtual stretch. And this is a left-hand side for the virtual work of spring system, and right-hand side, which is much easier. So for the spring system, principal virtual work become P and virtual stretch, and F1 U1 plus F2 U2. Okay? Here. You know why? Here, this is let's say this is x equal L is 0, x equal L. So here, this term become delta U1, right? This term become delta U2, right? How about this term? This is calculated from the internal force, right? So it become minus F1. And this become just F1, F2. So N is positive for tension, negative for compression. So here F1 make a compression, right? So we need to use negative. So final form is very simple. Looks simple. This is for just one spring. This is a principal virtual work for a single spring. And for a multiple spring case, so multiple structure, spring structure is a truss structure, like a truss structure. The equation can be generalized. Pi EI equal I equal 1 M FI UI. Here N equal number of member. M equal number of poles. This is really direct extension. So, for example, let's say we have a truss structure, something like this. Okay, we have a member. How many members we have here? 1, 2, 3, 4, 5, 6, 7, 8. Here, number of members is 8. And number of pulses. At each node, we have 2 possible pulses. 2, 3, 4, 5, 6. 6, 12 pulses can be applied. Any question? I think my presentation was too fast, so maybe. So what I did is, first I started from the general principle of virtual work, then I draw the principal virtual work for bar member. Then I gave you the principal virtual work for spring. Then truss system. So, but equation looks different in each case, right? But one thing very important is that internal virtual work, due to the internal force or stress, is same to the external virtual work due to the external force, right? Right? So internal virtual work and external virtual work is different. How to calculate internal virtual work and how to calculate external virtual work is different in each case, depending on the structure, okay, and system. But basic principle, internal virtual work is same to the external virtual work, is same thing for all the case. Okay, so now I'd like to give you an example. This could be very helpful for you to understand principle of virtual work, right? Example. Here we have a hinge and bar here. This is bar. That's a rigid bar. Rigid bar mean bar doesn't deform, no deformation. It can move, but doesn't deform. And length of bar is L. And here spring. We have a spring is attached. Spring, two spring is attached. A. And K1, K2 is a spring constant for each one. And here A. Force P F 0 is applied at x equal A. Now let me think about possible virtual displacement. So read by here, I'm gonna push this bar with a force F0. How this bar can, which kind of displacement you can have for this bar? There's only one pattern, right? Only one pattern. So this is the original shape. Is this pattern, right? There is only one pattern. So here, let's say here, virtual displacement, we can have only one virtual displacement pattern and displaced pattern also, right? One possible displacement pattern, one possible virtual displacement pattern. Right? So here, virtual displacement is theta. I'm going to use this virtual displacement pattern. And here, from here to here, delta UC. And here, delta UB. Spring is here. Spring is here. And P0 is applied here. P0, and this displacement is delta UA. In this case, I like to calculate the internal virtual work and external virtual work. Okay. Internal virtual work. Let's calculate internal virtual work. Internal virtual work equal. So, two spring will produce internal virtual work. For this spring, spring 1, spring 2. Okay? Spring 1, let's say P1 is a pulse. Internal pulse of spring 1, and E1 is a stretch of spring 1, P2 delta E2. This is an internal virtual work, right? Some of it comes from some of both springs, right? And here, P1 is a K1 U1, right? And how about the virtual stretch E1? E1 is same to this value, right? So let's say here this is a K1 U1. This become delta UB. Delta UB is same to the delta theta and this B, right? And similarly, here K2, U2, delta theta and L, right? This is internal virtual work. Now let's calculate the external virtual work. External virtual work. Internal virtual work is done by spring, two spring. How about external virtual work? Is done by external force P0 and virtual displacement UA equal F0 and virtual displacement theta and distance A. So this and this should be same, right? So F0 delta theta, okay, internal virtual work, K1 U1 okay, here again U1 equal K1 U1 equal theta B, right? Let's say the real displacement pattern is the same also. Then theta B, delta theta B plus K2 theta L, delta theta L. And both this is same to this. Here, in the left-hand side and right-hand side, we have a virtual displacement pattern there, here, right? So, left-hand side, theta, K1, theta, B square plus K2 L square theta equal delta theta F0 A, right? If I rearrange the equation, we can have this one. So in left-hand side and right-hand side, we have a virtual rotation, right? So we can delete. Then finally we can calculate theta. Set F0A, K1 B square, K2 L square. Here F0, right? then this becomes stiffness and theta is a solution. If we know the theta, we can calculate all the displacement. Okay, any question? It looks complicated. Yeah, this problem is very simple. So to calculate the solution, you don't need to use principal virtual work. Okay, but this is example to show how to use virtual displacement. So it's a very nice example by which you can show what happened. Okay.